Okay, so let's continue to the next part. You have seen so far the direct converters, buck and boost, and I already showed the switch implementation. So now let's go to this part in direct converter. Okay, here. So we make it full screen. Oh, what happened? Okay, so why we call it an indirect converter? This means energy stored in the intermediary, and then the intermediary transfer energy to the output. There's no direct energy flow from the input to the output, so we call it indirect. Here is the canonical cell for you to build in an indirect converter. So you just need to connect it properly. For example, on the B side, you connect it to the load side, and A and C you connect to the source side. You can see here V1 and V2. And then for analysis, it's not easy to analyze the circuit in this format, so we can approximate it to be this way, because the function of capacitor is to regulate current and voltage of the output, whether in this configuration or this configuration, right? So same goal, same purpose. Then we can just analyze using these configurations, which is easier. Of course, it can be the behavior can be slightly different. Anyway, we don't need to have the exact behavior of the system. Okay, so let's start analyzing using this configuration. So when you implement switch function in here, Q equal to 1, which means during the period from 0 to dt. So the switch here turn to the left, so you have this branch as a closed circuit, this branch is open circuit. Okay, so you don't need to, you can ignore this open circuit. Analyzing this closed circuit, you have voltage on the inductor, it's just the same as voltage of the source V1, okay, during this period. And then you switch to the right here, so you have the closed circuit on the right side, then you ignore all the circuit on the left side. So from here you have the voltage of the VL, voltage of the inductor, equal to minus voltage of this V2. Why minus? Because the current flow this way. When you switch here, you charge energy like this. So this one spin the magnetic flux, for example, this way. When you switch to this part, it's still spinning magnetic flux this way, which means current still flow from top to bottom, and then it flow like this. So you can see the current flow in the reverse polarity of the load. That's why the voltage VL here is minus V2. Okay, minus V2. Then again we can analyze using zero average value of voltage VL. So this area plus this area equal to 0. This is the plus area, and this is the minus area. Okay, you can cancel capital T, the period, and then finally we have the relationship between V1 and V2 in this way. Now let's see the behavior of the coefficient. Because d taken from 0 to 1, 1 minus d also taken from 0 to 1, and then d over 1 minus d can become 0 or can increase to infinity. Why? Because if d close to 0, you have 0 in the numerator and 1 in denominator. But if you choose d close to 1, you have 1 on numerator and you have 0 on denominator. Okay? So this ratio can be taken from 0 to infinity. To be precise, minus infinity to 0. Okay? Because we have the inversion. Alright. It seems this indirect converter is very simple and easy to analyze, and the ratio, the conversion ratio can be taken in very wide range, right? From minus infinity to 0. So you can pick up like 0.5, minus 0.5. Okay, now let's clear the sine inverse. The inverse. Reverse inversion. Inverse. Just say on positive side. So here you can choose whether 0.5, so it means you have buck converter because you have voltage of the output half of the input, or you can choose 2, 3, 4, 5 of the conversion ratio, so it means you have boost converter. So indirect converter can behave like buck and boost. Okay? It just you just need to choose the duty ratio correctly. Right? Okay, so it seems very good, right? Simple, easy to analyze, and can convert the voltage in a wide range. Where for buck and boost, this one. Okay, there are the other type of indirect converter, but I'm not going to explain one by one I only explain the most simple one to get the introduction. Anyway, you can just know the name of other type of indirect converter like CUK, C-U-K. It is indirect because you have the storage element in between here, like capacitor. Another one is SEPIX. Also you have storage element in between capacitor C1 and R2. So these two are more complicated in terms of analysis, and if you become specialist in, or you're very interested in power electronics, and you must look at these two converters as well, because it also these two also have wide range of application. Okay, now let's come back to the property of indirect converter that have large range of conversion ratio from minus infinity to 0. So why don't we just always use indirect converter versus direct converter? I already saw a moment ago that it's easy to use. Conversion ratio can take it at a very wide range. So why? Yeah, there are two problems, not really problem, but disadvantages of indirect converter. One is the sign inversion, because the conversion, the output has negative voltage. It can be fixed. You just need to carefully switch the polarity, okay? Or you can build another type of amplifier that can also have sign inversion. Okay, so inverse and then you inverse again, it becomes the same as input. How about another disadvantage of indirect converter? Yeah, the second one is device and component stresses. stress means you work too much, right? Yeah, so electronic component can also affect from the stress. I mean, if it works too much, yeah, it works over capacity, for example. So let's analyze and make comparison between indirect converter and direct converter in terms of component stresses. From analysis, we can prove that the current on inductor, the absolute value of current on inductor is the sum of absolute value of current I1 and I2. Okay, so if you want to convert to very high current of I2, or you want to get large current I2, it means you drop the voltage. Okay, and then you have component stress IL is very big, right? Yeah, why we can just use convention. Why inductor should have like should sustain large current, because it switches from one to another, right? Let's say it, in order to switch to the output I2, of course at least it has the capacity to have energy that can transfer current I2, but at the same time it's also need to charge, right? Alright, so in order to have always have I2, it need to have current IL, which is I1 plus I2, because it also need to store some energy to the capacitor. And again, for the voltage, okay, for the voltage on capacitor, the absolute value of voltage on capacitor has to be the sum of absolute value of V1 and V2. Okay? Sum of absolute, not absolute of sum, right? So the component stress is, let's say if you want to boost the converter to have a high voltage at V2, then the capacitor needs to sustain even higher voltage, which is absolute V1 plus absolute V2. So it must be it has a lot of stress. Okay. So to design an indirect converter compared to direct converter, you need to choose large inductor and large capacitor. If you compare to direct converter, actually the component stress, for example on capacitor, the voltage on the capacitor is just the maximum between V1 and V2. For buck converter, V1 is bigger than V2, so the component stress is just the same as V1. For the current on inductor, current on inductor equal to the maximum between current on switch Q or current on diode. So the mark between these two is I2. So for buck converter, you have larger current at the input or at the output. Okay. For boost, component stress VC is the same as the maximum voltage, which is V2, and the stress on inductor IL is the same as maximum current, which is I1. Okay. So actually for either type of direct converter, VC and IL is just max between V1 and V2. IL is max between I1 and I2. Okay, not sum of both of them. Okay. So let's say you convert the voltage not too much different, like let's say V1 and V2 are almost same, and then okay, let's say it's better to say it this way. Let's say V2 is twice as big as V1, then component stress of direct converter is just V2, which is twice, like if you consider the size of capacitor, it's like let's say the size is 2, but for indirect converter you have V1 voltage, absolute V1, absolute V2 add together, so you have like size up to 3, so 2 versus 3, right? But if V2 is like 5 times V1, and then you have 5 plus 1 becomes 6, so 5 and 6 not so much different. So actually the component size will be very different if the conversion is not too big, conversion ratio is not too big, so the size component will be very different. The next part about report components and filter sizing. Now you see the term filter again. Report component means in ideal case we analyze, we consider only purely constant voltage of the output or on the capacitor parallel to the output, and also the constant current on the inductor. But in real life, in real application, you try to choose a small storage element as possible, because you want to save the space, you want your design looks nice, right? So we need to live with report. I mean, we allow some fluctuation, okay, in the range that your system still can operate. So that fluctuation is called report. Filter sizing means you're trying to choose the right, the most satisfied component size, storage element size, like inductor, so like how many millihenry, a capacitor, how many farad, maybe microfarad, something like that. Okay, so component size does depend on report. So how to approximately calculate report? So you are going to see the process to calculate a report, but it's not exact, it's just approximately. Yeah, just approximation. So first, now because you have two storage elements, and you have seen so far that if you derive the governing equation for all RLC circuit, you will get second order differential equation, which is second order. So for analysis, in order to make simplification, to eliminate the second order effects, eliminate second order effect on capacitor voltage report, we assume infinite value of inductor first. Okay, so when we want to analyze the report on capacitor, we assume that the inductor has finite value of inductance. So there's no report from the current from the inductor I1. Okay. So if no report here, we can consider it's just constant. Then we can analyze just switch on and off. So it's easy. Okay. Like I said earlier, it's just approximation, right? So we need to make some assumption in order to reduce this complexity. Similarly, in order to analyze the report on the inductor, okay, current report on inductor, then we need to assume that capacitance of capacitor is infinite. And second assumption is that all ripple voltage is across in inductor. And okay, so here ripple component and filter sizing for capacitor. So we already assume that inductance has infinite value, then I1 is constant, and then the current on the ID, it depends on the switch here. When you switch on, the current flow this way, so no current in here, so you got 0. Okay, so this is ID is for this one. Okay, no delay, it's okay. And when the MOSFET is switched off, current I1 fully flows through diode. So you have I1 here. Okay, so the actual waveform of ID actually like this, because inductance is not infinite. Right? But anyway, we approximate like this, and it just repeats over the period T. So if you calculate the mean value, you get this. Okay, it just the duty on this period, during this period, right? And then consider the what do you call this, ID-TL. ID-TL is just ID minus its average value. Okay, so control P, ID-TL equal to the original ID minus its average value. Okay, so it's like you drop you offset this waveform downward to have the area of this and the area of this are equal. Okay, yeah, have these two area equal. So this 0 is offset to minus this average value, and I1 offset to be this value. Okay, so from here we can find the ripple voltage on capacitor using the relationship between current and voltage on capacitor. Yeah, because here we assume that all this ripple, so this is kind of a current ripple. Okay, current ripple. Okay, current ripple means the average value current here, we have average value current here, flow from here. Okay, so this is assumed to be just go to this resistor. Okay, but actually this value will add some ripple to be like this and like this, not just straight like this, but it adds some ripple like this, or so it sometimes it's higher, sometimes it's lower, but this higher and this lower are assumed to be just go in and out through the capacitor. You got the point? Then we always have the constant current to the load. Okay, this is the second assumption actually. So now let's look at all the ripple current here, plus and minus here, just go to this capacitor. So we analyze only this circuit, this branch, this loop, which means we have ID, ID-TL, equal to C derivative of VC with respect to time, right? And then we can find VC. We can find VC as an integral. I can have on the right side maybe. Yeah, here. Then we can have VC. To be precise, that delta VC, because we only consider the because we already have the average VC is the same as the output V2. So if we consider the report, it means just we subtract the actual by the average value. Okay, so that's why we write down as a delta VC. Okay. Yeah, because we use this one. In Samsung, this one also delta, right? In Samsung, it's kind of delta I. So here, this delta I just go in and out from the capacitor. Then we want to compute like how much is the fluctuation of VC with respect to the average value. This is average value, but it can go higher and then go lower. So from this integral we finally have this, and then we want to compute C. So C equal to this in terms of duty ratio, period T, and the report that we allow to have in the capacitor, and also I1 here. Okay, so actually when designing, when choosing the filter size, here filter sizing, right? Filter sizing, which means when you choose capacitor, you choose inductor, you need to choose report delta VC, which means how much voltage you allow to go up and down on the capacitor. Okay, so the designer decide to choose. All right. So here you, from this equation, you get C equal to, supposed to equal to this, right? But anyway, the bigger the storage element, the smaller the report. Of course, to have a good performance of our converter, we want everything smooth, right? I mean small report. But in here let's say, okay, now let's choose report. We allow to report to be delta VC, but cannot be larger than this. So it means you need to choose C which greater or equal to this term, because bigger C the better, right? Maybe just you wonder why you got the sign bigger. Anyway, the bigger the better. Also, in terms of real design process, when you calculate C and you look at the commercial capacitor, maybe you cannot have the one that has the same specification as your calculation, right? Should be different, and you need to choose the bigger one, not the smaller one. Similarly, to find the report of current flowing in and out, report current flowing in and out to the inductor. So first we assume that capacitor here C1 is big, so that there's no report of the voltage in here. Okay, this one is big enough so that voltage will be constant in here. So then the voltage on the switch VH depends on the state of the switch, whether it's on or off. So we plot VH here. When you switch it on, it's short here, then VH is 0. When you switch it off, open, then the voltage just parallel here, it equal to voltage of the output V2. Okay, and again here actually the actual look like this, because C, we choose limited C. But anyway, we analyze using this idea. Then we just try to find the fluctuation of voltage with respect to the average. Okay, so average VH at here. Then we find VH-TL. Yeah, again VH-TL is kind of delta VH. Okay, because it equal to VH itself minus its average value. So then we can make an analysis here. The current flowing through inductor, you have relationship VH-TL equal to VL. So it is L DIL over DT. Call it ITL. Okay, call this one TL as well. And then you have ILTL as 1 over L integral from 0 to dt. Yeah, you consider this period, this period. So you use this value. VH-TL dt. So during this period, this value, okay, which is 1 minus d times V2. Okay, so finally you can calculate this integral. Then you can find L should be greater or equal to this term. Okay, the bigger, the better. If you choose L equal to this, it means the report is exactly like this. If you choose bigger L, so then the report will be like this, smaller like this. Okay, which is better. Any question up to this point? Udam? No question? So far so good? Boromai? Is it okay? Smiling means okay. Okay, so so actually energy storage sizing L and C, the physical side determined by some factors. The first one, energy storage. Second one, losses, because let's say to have your converter operate normally, you need the amount of energy stored in your components. So we only consider the net amount of store, right? So the capacity, so one component can store up to some amount, but at the same time it lost, right? So then we should calculate using the net store of energy. And then another factor is packing constraint, because some inductor looks like a round, some inductor like long, some of them it just looks like solid state. Okay, so it depends on your application. You need to choose the appropriate one. and also the material properties. Okay, material property also affect to the how it can sustain to a certain temperature or working environment. And next we're gonna see the analysis on in terms of peak energy storage requirement. We use this terminology. Okay, you can see here the term ripple ratio. So when you design a converter, you know that you know the source that you have, for example battery 24 volts, and then you know that the load operating at a certain voltage, for example 12 volts or 5 volts or 3.3 volts. So you know voltage, right? And then let's say, okay, you want to choose capacitor or inductor, and you can allow the ripple, okay, ripple value to a certain value. Then you can calculate the ratio of, okay, we call ripple ratio. Let's say you want to design a 5 volt at the output, but then you can allow 1 volt up and down. Okay, so it means it can go up to 6 volt or it can go down to 4 volt, right? So it means that tau V is 2. Yeah, the tau V is 2. The tau V over 2 is 1 volt. So 1 volt over 5, then you allow ripple ratio to be 20%. Okay, to see a clear picture, let me give, let's say you want to choose V2 at 5 volt. Okay, V2 at 5 volts, and then you allow it can go up to 6 volt or down to 4 volt. Maybe not too like this. Okay, so here 4 volts. So the tau V is, this is delta V. Okay, so the tau V equal to 2 volts, which means the tau V over 2 is 1 volt. So the tau VC over 2 is 1 volt, and you have the average voltage VC or V2 same. So you have 5 volt here. Then it means you use 20% of ripple, right? 1 over 5. Okay, so you decide to choose how much the percentage of ripple ratio. Same thing for OL or calligraph L. And okay, and so here the way you compute the peak value of voltage or current. So H here represent voltage or current. Okay, this term PK represent peak, PEAK, peak value. Okay, delta H means you measure from here to here. Okay, delta H. So from here to here, just delta H over 2. PP, the term PP means peak to peak. This also peak, but the peak, yeah, the lowest peak, maybe it does not sound correct. Okay, anyways, just call it from peak to peak. Okay. So let's say this is voltage. You want to write down voltage at the peak here. You have the average value here, VC, and then plus delta VC over 2, right? So finally you can write in terms of ripple ratio in this way. Okay, take VC is in parentheses like this. Yeah, peak value, and here average value times 1 plus ripple ratio. Same for IL. And now you substitute the term, yes, substitute some here you have the term VC, data VC and VC from here. Yeah, you have, yeah, V2 is same as VC. Yeah, so you have this and you have this, then you can reformulate it to be in terms of a ripple ratio or C or OR. Okay. Okay, so the process to calculate filter size is like this. First, you know the source that you have, it means V1, and then you know that the operating voltage of the load V2. Okay, and then you need to know the current, or you can say maybe you know the power first, or maybe you know the current at the load first. So you need to know I2, right? You need how much current your load need, and then you can make assumption like what is the efficiency of converter. So you choose efficiency 85%, 90%, for example, and then you can calculate I1. So now you have I2, V2, I2, you have V1 and I1 by making assumption on efficiency. Okay. So now you have all these parameters. Then okay, you choose. Okay, then you choose ripple ratio or C and OR, like how many percent. Okay. Okay. 20%, it means 0.2, right? 20%. Here 20%. Yeah. This is an example of RC or RL. And in order to convert from V1 to V2, you can calculate the duty ratio D, right? How about period T? Period T, you choose the frequency of the pulse width modulation. Let's say 1 kilohertz. 1 kilohertz means in one period, the pulse, it generates 1,000 pulse. So one pulse, it takes just 1 millisecond. So T 1 millisecond, like in this case. Okay, so through this process, you can calculate C, also you can calculate L. This is how you choose filter size. Okay. So next week I'm gonna show one Excel table that show the process, the step that you need to take in order to find or to compute the size of filter C and L. And then you can make an experiment on the boost converter that we built from scratch. Yeah, we are using junk component. Okay, but anyway, it worked as we expected. It's fun to work on it, right? Yeah, so you will see next week boost converter. If we have time, we also work with buck. And the energy storage for capacitor. So this is to verify that when you choose one capacitor, you need to see the specification, like how much energy it can store, and from your calculation you require it to store this amount of energy. If it's satisfied, then you can use it. Okay. And now we just make some analysis, like the energy storage, that energy storage increase with what factor? Okay, what time? Look at here. Look at this formulation. I don't explain it in detail. Just explain the final one. D is duty cycle. P is the power of the output. I have here switch frequency, the PWM frequency, like I mentioned earlier, for example, 1 kilohertz. In some application, people may use up to 62 kilohertz, but not more than that because it can interfere with radio frequency. So this is frequency and this is ripple ratio, okay, for capacitor. Okay, so from this formulation we can say that capacitor energy storage increase with conversion ratio. What does this mean? Conversion ratio means depends on D here. If D is big, conversion ratio, it increase depends on D. And another one, power level, P0. Power level, P0. If power high, we also need capacitor that can store higher energy. And then it decrease, right? Energy storage decrease with what factor? Switching frequency. Yeah, this is a good one. If you use high frequency, which means you need to store energy in a very short period of time, and then you release. I mean, the component, not you. The storage element just need to store energy in a short period of time, and then it transfer to the other part. So it doesn't need to store so much energy, right? If you switch very fast. This makes sense, right? And this is the way that we can design very, very small electronics, but it can transfer or convert large energy. Okay? So in the past, when the speed of microcontroller was not so good, electronics device need to be big. The size, storage size, every other thing need to be big. But with the high speed of microcontroller that can switch very fast, then we can reduce the size of electronics device or filter size. Also, the energy storage for direct converter is always less than that of indirect converter. Okay. And I think, this is just summarize of what I showed earlier. This part is about switch stress parameters. This is not how exactly the it's not kind of this calculation does not follow like natural law or something, but it just terminology that how you can simplify parameter so that you can easily compute, easily calculate. Then based on that, you can select component easily. Okay, so that's why here we call it a metric for switch side. So this is qualitative only. Qualitative means just some metrics that you can use a certain terminology to simply calculate the parameter so that you can follow a certain process to select your components, right? So the switch stress components, switch stress parameters is the product of the stress in terms of voltage, and then the stress in terms of ripple ratio, the stress in terms of current. Okay, ripple ratio, you have ripple ratio on capacitor and ratio on L. So this is kind of like you cover all the factors. Okay. So it's kind of metric to qualitatively analyze the stress on your components. Let's say you design this converter in this way, and you design that converter in that way, and then you compute the switch stress parameter. If you see that the value of switch stress parameter for this one is larger than that of this one, it means you have the risk that this one is more likely to be broken earlier. Okay, something like that. But you cannot use it to say exactly when it's going to be broken, when it stops functioning. Not like that. Unless you do some experiment or many, and then you can have the baselines. Okay, so lots of experiment, lots of data can help you to make table or something, or a library or lookup table, and then you can refer to it. Then you can predict the lives of your converters. And from here, what we can conclude on the switch stress parameter is that it gets worse for large power, large conversion ratio, and large ripple. Okay, this is the very simple, right? Just three key things when you design, when you choose parameter, and then you feel you have some, because we say qualitative, right? You can get a feeling that your switch maybe gets so much stress or not. Okay, so let's finish our lecture for today. If you have any question, I can take one or two. We still have 2 minutes. Sila, any question? No question.